Hello. So welcome to my lecture. I'm a little jet lagged, so if I look sleepy or something, don't mind. It's also 8 a.m., so it's really early. 1 second, just adjusting the mic. Okay, that's better. Can you guys hear me at the back? Yeah? Can you hear me? Okay. All right, so how this lecture came about, Francois asked me to do a lecture for the deep learning course, and I'm like, oh, sure, I'll do a PyTorch lecture like I always do. But then Francois was like, no, like all of my homework's already in PyTorch, you know, the second last lecture, if you come do a PyTorch lecture, like it's going to miss the point because the students, they already know PyTorch. And so I'm like, okay. I could talk a little bit about what I experienced after graduating from university and then started a deep learning job and how, like what I learned in university, somehow very little of it applies to the real world in sum total. It's like you learn all these tools, but then how do you apply everything you learned to a new problem? That's something I want to talk about first. So let's say you did this course, you learned unsupervised learning, you learned supervised learning, semi-supervised, generative modeling, on images, text, on MNIST digits. You have all this, like how to do every single one of these. But then, let's say you want to water your plant. You want to build a robot that every day it goes and takes some water from your sink, and then it pours the water into the plant. It's very simple, right? But you learn deep learning. You should be able to do something like this. It shouldn't be too hard, right? But then you start to think about how to approach this problem, how to break it down into sub-problems. It starts getting more and more difficult to approach. So I want to just walk through how I think about it when I'm approaching like a typical deep learning problem. Something simpler than watering a plant, which involves robotics and stuff. I won't touch on that. But typically, you can see this as writing your function f, which can be a neural network that you train, or it could be some machine learning model that you build. It takes some inputs and it gives you some outputs. And one of the fundamental things when you start doing neural networks, especially, is you have to think really hard about what is your input and what is your typical output. Oh, is my input an image? Is my input some video? Is it text data? Is it some signals from the Large Hadron Collider? Like it's all. It's very important, especially in neural networks, because the architecture of your neural network is very much sort of fitted to your inputs and outputs. And this is very important. The reason you do this is to give the neural network a prior of what your inputs are typically. So if it's an image, you apply a convolutional neural network. You say, oh, I see these locally repeating patterns, and that's something that's pretty much common to all images I can think of. So I'll apply this big prior to my neural networks. Instead of having a fully connected, like a multi-layer perceptron network, I will actually apply a convolutional neural network. And that improves the data efficiency of your neural network. That decreases the number of parameters you have to learn. And that also means the amount of data you typically need to train this neural network is also reduced greatly. So depending on the input you have, you should typically think about how to encode more and more of that prior into your neural network while keeping the concept pretty general. So as I mentioned, the more prior you actually encode into the network, the lesser data it further needs. And to give you a little bit of backstory of, or like sort of practical sense of how people typically do things, let's say your neural network is an image or a video. It's obvious, you just put a connet and then you're done for the day. But let's say your neural net, your input data is actually some Excel file that is sitting, which has all these features that people have extracted from like a large system, some like large company system. That's like one feature on like whether your customer buys milk every day or not. One feature on like whether which neighborhood like a person lives. And like, so typically, let's say you have a big feature vector of say 100,000 sparse labels that give information on like a customer or like some sales or something. Then using a convolutional neural network won't help because there's no locally repeated patterns. You would typically want to use a fully connected neural network, but let's say you have like 1 million features. Doing a matrix multiply of 1 million features with like, let's say the second layer is 1,000 hidden units. That's a very large matrix multiply. So in such cases, your like efficiency problems kick in. You would want to do something like a sparse matrix multiply where you know, even though there's 1 million features, typically for each particular entry in your data set, only like say 20 features are actually active, are ones, and everything else is zeros. So these are things that you can think of as priors for, not for like the, not adjusting the parameters of your neural network, but for just efficiency of computation as well. And the other thing that often gets lost is choosing your loss function typically matters much more than you can think. In the real world, you don't get a clean academic data set where like everything is like, oh, like if you have a label, it's for sure like the right answer. Typically, you have noisy labels. So you know how you learned that in gradient descent, if you have a large gradient, that typically means that your neural network doesn't know the answer correctly and you should adjust it. So, like, if you have noisy data, if you have a large gradient, that just means that it also probably means that your label is just wrong. So then you can have some kind of loss function that thresholds between, like, if your gradient is bounded between like this norm and like this neighborhood of like if the gradient is not too large or not too small, only then you're trained with that sample. So you typically come into seeing if like these sampling schemes work, like use the hardest samples lesser or more, or like do some kind of importance sampling. And also like about the loss function, let's say you want to do a task. Let's say you want to do some classification of like cats versus dogs, but you only have 10 cat images and 10 dog images labeled, but you have like a lot of unlabeled images. Then you want to use some loss function that does unsupervised learning and then supervised learning online. So choosing the right function matters a lot more in the real world, where you have noisy data, where you don't have labeled data, and labeling data is expensive, not just for money reasons, but like maybe you have like some deadline and you're like, oh, within this deadline, I can't even get the data labeled. So all of these things come into play. And so you learned all these great techniques in the course. From the lecture list, I saw pretty much all of like the latest models covered. You learned things like YOLO and ResNet and I don't know, everything under the sun you have probably covered. But if you go to a lot of startups and you see what they're probably using scikit-learns like linear regression or logistic regression. And it's not simply that you go there and say, oh, but I know how to use deep learning. It's much better. If you actually try to use it, you're probably going to find out for that particular problem, it doesn't matter like whether you use simple method or a more complicated method. It's like where deep learning really shines is when you have a lot of data, or where you can figure out how to build a large augmented data set, and you can build like the right neural network with the prior. Like even baselines like k-nearest neighbors are typically very useful and like used a lot more in practice than you actually think. Now I want to walk through some scenarios and see how we will like approach a real world problem. So I gave you like about what 3 or like 4 slides of three slides of like, okay, how do you approach a problem? Think about the inputs, think about the outputs, and then think about how to encode priors. Whether you should do unsupervised learning or not depends on how much data you have and stuff, right? So I'm like, okay, let's go through some scenarios. I pulled up the Kaggle competitions page, and I was looking through the different kinds of competitions you have, and I want to just pick each competition, and we can walk through like how we would generally solve these competitions. So let's take the first competition. It's from like our neighbors here at CERN. It's basically a particle tracking challenge where they have, I don't know like exactly, so they have they have tabular data as input for you, which means like in the CERN pipeline, from what I remember, you record a lot of data about like the particle collisions, and then it gets filtered through a really high-speed FPGAs, which do some kind of feature extraction. They kind of pre-filter what is useful features and what is not useful features. And it could be maybe like 10,000 features that are sparsely activating based on some heuristic physics function. And then this is the particle tracking challenge is, can you, in this collision, when this collision happens, you want to track particles across time. And I presume the data has some time series involved, so it's probably tabular data with some time component. So let's go through like, let's say you have about this data, if you think about it, it's feature extracted, but it has a time component, right? So could someone tell me whether applying a convolutional net applies here in some dimension or not? Is there some kind of local structure that is preserved across some dimension, whether space or time, in this data? Yes? No? Yes. Over time, there is definitely. Over time, you basically have like these. You can think of it as like a fast-moving video or a slow-moving video, and when you're tracking a particle versus tracking another particle, you probably have like similarities you can capture. So you probably want to apply the convolution over the time dimension. And depending on like how they gave the data, let's say they gave the data with also like spatial coordinates, like in some like 3D volume, then you can also apply like a 3D connet. But another challenge here is the data is probably very sparse, because remember they pre-filtered only focusing on the useful parts of the collision and not like removed all the non-useful parts. So you might want to apply what is called a sparse convolutional neural network if you want to get like the best data efficiency, not just in terms of like the number of like parameters or capacity of learning, but also from like the computational perspective. So one of my colleagues at the Facebook Paris office actually has written like 2 or 3 papers on how to efficiently do sparse convolutional neural networks. And there's actually a PyTorch package they wrote called SparseConNet, where if you have like very sparse, like tabular-like data, then you can actually do this kind of problem much more efficiently. And for a particle tracking challenge, what do you think the loss function would typically look like? If you think about it, you have to track a particle from one time frame to another. So let's assume we are going to slice the video up, and we're gonna track these particles through time. Do you think it should be some kind of a mean square error of over all particles, or should it be some kind of like a GAN loss, or is it a classification? Any thoughts on that? Anyone want to raise their hand, or should I pick some people? You wanna take a crack at it?
I would say, yeah, that's the loss because it's a distance.
It's a distance. So a mean square loss for each particle, or so the loss generally is a scalar value, right? So do you want to just sum it up over all particles? Okay. So that's typically a reasonable loss if you want like very blurry track. Like it's based on Kale divergence like metrics. The GAN loss will probably, I don't know, like I haven't looked at the actual data, but the GAN loss probably will track some particles really well, but it'll completely collapse on some other particles. It's hard to tell. But that's the TrackML challenge, like I took a crack at it. Now, the second one is actually ads prediction, which is very different. It's again like it's tabular data, but they also gave image data and text data, typically of like the content of the ad itself, I presume. Right? Is it? Yeah. So you have to classify whether an ad gets clicked or not, and under some metrics. And the loss function in these cases is usually defined by the challenge itself, and it's something like you take a user's embedding, and then you take the ad, and then you have to compute whether like the user will click the ad or something like that. Or you typically have to re-rank the ads. You have like a lot of ads, say like 1,000 ads in your system, and you have to rank them per user on like the top 10 ads that the user will click or not. And in this case, if you think about it, for the image data, like just the visual image of the ad, you want to train an embedding that you can take a dot product with the user embedding on whether the user will click the ad or not. So like you'll have a connet that goes from the image to like some embedding of size, like say 128 or something, and the user embedding could also have some kind of projection layer that goes from like its dimensionality to some 128 embedding, and the text data, which is also like probably the contents of the ad, you'll run them through some like word embeddings, which were covered in the course, and then like from the word embeddings you would also get some like final embedding, and then you would take like you'll have a linear layer that sort of takes in all these three inputs and computes like classification of whether you click it or not. And then you backprop to the whole thing. So over time, as you train, your click prediction will get better. The third one is very different from the first two. It's a video segmentation challenge, which means you have a video. You typically want to segment maybe like where the stop sign is. It's for like does it say self-driving car? Yeah, it says like image frames captured by vehicles. So like, a car is driving, you want to segment the images, maybe like segment like per like where the stop sign is, like per pixel classification. this was covered in your course, so you would just take what you know from the course, just apply that straight to this challenge and see how you fare. Like in the next list, they're all like fairly, the first two one are classification, so you would do what you learned in the course again. You would just take all this data, put it in the format that you know how to run your ResNet 18 or whatever, and it will work out. The third one is a landmark retrieval challenge. So it's not a simple classification loss. It's you have to train embeddings that you can retrieve very efficiently. So it's like, okay, if I'm given a new image of a landmark, can I extract from features from that image and then do like a lookup with all the landmarks I have in my database? You can, so one question I have is, let's say you have 100 landmarks in your database, right? And you have your training data that covers all of these 100 landmarks. Would you treat this as a classification loss, or would you treat this as some kind of like cosine embedding loss, where like whenever you get the second case, what I'm talking about is when you get the image, you would extract some embedding out of the image and then do a dot product with all of the landmark embeddings that you have trained in your database. So if you have 100 landmarks, would you simply just classify like each image directly into one of 100 images, or would you do this like lookup kind of a system? Any intuition on like which would be better for like this scale? Let's say you have 10. What would you do? Let's start with 2. Okay, I want to raise of hands. If you have 2 landmarks in your database, would you simply do a classification loss, where like your output of your neural network is whether it's landmark 1 or landmark 2, or would you do an embedding loss where the output of your neural network is some embedding, and then you do some nearest neighbor lookup of that embedding with your landmark embeddings and find out which one is the closest? For option A, classification loss. All right, so that's most of you. And if you just have 2 landmarks, that seems great. Let's say you have 100 landmarks in your database. Would you do classification or the other kind? Would you do classification? How many would say yes? Okay, 1 says yes. Okay. If you have what's the, okay, I want to understand what's the reasoning for saying no to the 100 landmarks case. You wanna tell me what you're thinking?
I think maybe with the embedding, it would be more able to really get the difference between the landmarks instead of just a classification that maybe doesn't get the features of the landmark.
Okay. I want to hear from like a few more people. Maybe you wanna talk?
With binary classification, it's easy because you just have 2 cases. If you do a model to look around, there's so much complexity.
Okay.
In something that is very simple, but when you have 100, maybe close landmarks are similar, the embedding, so you can capture this type of thing.
Okay. Like your intuition tells you it's harder to classify 100 embeddings, but let's take a look at let's think about like in what case it gets harder and what case it gets easier. It depends on several other variables that I haven't even told you about, like how big is your data set. Let's say you have 1 million images, each representing the landmarks equally. Actually doing a 100-way classification is actually not that bad, like from like an optimization perspective or whatever. You have enough data, you can like your network will train fine. Actually the classification loss will do better. This is something, if you look at the ImageNet data set that was covered in your course, it is 1.2 million images over 1,000 classes. the classification losses actually do better than like the embedding losses. But if you try to do the same thing for CIFAR 10, which is 10 classes, CIFAR 100, which is 100 classes, but much lesser data, only 50,000 images or so, you'll probably start seeing that, it's the other way. Let's say you have even lesser data, like not even 50,000 images. Let's say I gave you like 10 images or something. Then it depends on like how you construct your network. It depends on like the size of your network and all of that. But I would go for like a nearest neighbor prototype loss. Like in that case, when your data is not sufficient to there is actually like principled ways of thinking about it. You can look at there's some work in the NLP world where they talk about if you have like a fully connected layer that is like say 4096 dimensions large, then let's say your vocabulary size is actually like even larger. You have like 100,000 words in your vocabulary. Can you do 100,000 way classification? And it depends on it depends on the 4096 layer. That's your second last layer, becomes the bottleneck, and that's depending on like what optimization algorithm you use and like and just the rank of your Jacobian that you can pass through from like this 4096 layer. If you ever go get a PhD, you can start thinking about this in more principled ways. But intuitively, I would say like the linear model you should think of is like how much data you have, how much can you like sort of transfer model it or brute force it. So can you take a pre-trained ImageNet and then do a large part of transfer learning, especially if you have lesser data, and do some kind of nearest neighbor embeddings. Or if you have enough data, then simply do like end-to-end classification. So the other examples here are not too different from what I already covered. So I would just take a pass at that. Let's see how we're doing on time. Okay, so we have like another 15 minutes. All right. So one of the clear examples here that I want to just take a crack at is if you look at the second last one, it's an image classification, but it's over 8,000 classes, right? So now you're getting into this territory of like, okay, now it's not 100 landmarks, it's like 8,000 landmarks. Now, like, what do you do? One data point I have, well, I don't know the obvious answer, even though I work in the field. It depends really on several factors. But one recent work I wanted to talk about was my colleagues at Facebook. They took 50 billion public images from Instagram. And on Instagram, people use hashtags, right? Like they say hash pizza, hash tasty, or something like that. And like for each image, people give a lot of hashtags. And I think they had as many hashtags. I don't remember the exact number, but they were like 1 million hashtags or something. And also people hashtag things with the wrong label all the time. So you could just be like hash doggy, and it might not be a dog, and like that's pretty normal. So it's very noisy labels, but you have a humongous amount of data, and so like the way they approached the problem is they had to think of like the right loss function that can run from all this noisy data with almost like 100,000 useful hashtags, I think. And you should if you get time, I will send you the paper to the mailing list. It would be interesting to see how, like at scale, at a very different scale, the problems were approached from like than, let's say, doing a cipher 10 classification. One of the interesting things there is once they trained their network, they actually did a transfer learning task on ImageNet, which is now only like 1.2 million images compared to like the 50 billion images that they trained with. And they actually saw a bump in the ImageNet accuracy compared to like directly training on ImageNet itself. It's like, so the neural network learned better features over all these like 50 billion images than that generalized to the ImageNet data set specifically than if you simply train on the 1.2 million ImageNet images directly. Which kind of shows how important generally transfer learning is. Because once you try to apply neural networks to any typical problem that you would pick, on average, you will find out that you don't have enough data, like not enough that the neural network needs. So like the most common thing people do in the industry is take a network that has already been trained on some generalized task like ImageNet or something, and then transfer that network, chop off the last layer, and then retrain the classifier on like a different smaller task with lesser data. This is very, very important practically. So in summary, I think what we looked at, the kind of dimensions we looked at are think about what data you have available. If the data set is too small, think about doing unsupervised learning. You can do unsupervised learning in like many ways. You could have a large set of unlabeled images, and you could do what kids do. Kids, like babies, they actually do, not only babies, like general humans, they do a lot of really good unsupervised learning. There is a paper from CVPR 2 years ago, which actually, to learn these generalized embeddings that can generalize over new supervised tasks, they took a large amount of images and then they made it into puzzles. You know, like the puzzles you play with, like the cardboard puzzles. You take an image and then you like break it up and then you mix it, and then the puzzle is to put back the image. So that is unsupervised learning, right? Like it's a game that's self-supervised. You defined a small, cute loss function for yourself, and then as the network plays this game, it learns good embeddings from images that then, if you have too small of a labeled data set, you can take such a network and then transfer it over to your task, because it has already learned some things about images. Maybe it learned how to cluster objects already or something, and then you can apply it to your particular problem, which might transfer well. You'd fine-tune the network for one epoch over the last layer, and it might work out pretty well. So if you have too small of a data set, typically use unsupervised learning. I just gave a very creative example of unsupervised learning, but you have like many of the standard methods that actually Francois covered in the course, like generative modeling. You can train a GAN or like a general VAE and use that as some kind of prior to your final model. If there's too noisy of a data set, you want to think about how to regularize your model to not train on, like somehow have a heuristic to detect what is noisy, like what is like not, what data is not fitting to what the network is learning as the true label, and like give some relaxation there on, oh, it might just be noisy data because my loss is too high, but it somehow doesn't correlate with what I think is the problem. Maybe the norm of the gradient is too high or something. So typically you want to regularize smartly there to deal with noisy data, which is actually very common in the real world. You want to think about the type of input and output. You want to think about what is your input like, so that you can build a neural network that fits for your input, that can encode some priors that your input has. If you have time series, you can apply convolution layers, you can apply like recurrent networks like LSTMs, and that is quite important. And this actually equally applies to outputs as well. Like, I mean, I generally covered, okay, what is your input like? But if you think about it, the same principle applies to, let's say you have an input which is some one-hot encoding of like whether it's a cat or a dog or a lion or something. It's just like 10 numbers, and the output is actually an image. Like in generative modeling, you have this, right? So at the input part, you would put fully connected layers, but at the output part, you would put more emphasis on putting convolution layers, because here, the output is where you have to give the prior of a convolution because you're trying to produce an image in generative modeling. At the input, doing a convolution layer wouldn't help that much because it's some kind of discrete sparse input. Typically, if you have text processing, people use representations like bags of words, which is you simply take a sentence and then you do some running window where for each window of, let's say, 3 words or something, you will just sum up the embeddings into what you call a bag of words. And so for each window of samples, you would just like sum up the embeddings of the local neighborhood of words. And this works pretty well. Bags of words combined with like a nice classifier actually works really well in practice. If you do any text classification that is not, that doesn't have a lot of data or not is super specialized, you would actually like use these like sparse text models with with the input features being bags of words. And then LSTMs, which are a type of RNNs that you probably covered in your course, are actually very popular. But more recently, actually, you're seeing in all of these text models, the LSTM trend going away. You're seeing either convolutional neural networks replacing them even for, say, tasks like machine translation, or you're seeing this type of network called memory networks, or like they're called in different names based on like which paper you read and who thinks they've invented them, but they're called memory networks. They're called attention is all you need, like transformer networks, and they're all the same thing. It's basically you don't have a convolution. You just have a fully connected followed by an attention model, which locally looks at what it should focus on. Was this covered in the course in general? Okay, so but in general, like the LSTM RNNs are sort of going out of trend. Maybe they will come back into fashion again in 2 years. I don't know. Practically, if you're working at a very large company, you probably won't do a lot of feature engineering. But if you're working at a small company or just with a problem that has like very little data, you would do feature engineering where you would first try to extract a more useful features from the inputs you have rather than try to simply do an end-to-end neural network, because the neural network probably doesn't have enough data to do a good job at it. So if you have like say 100,000 features of your tabular data, then you would try to extract the more useful features from it, like just thinking intuitively, finding heuristics, and get that number down to maybe like 200 useful features, and then you will push that through a neural network. This is like very common task that people do. The last thing we discussed is just having very good baselines is important. Like the standard methods that in machine learning that have been around for a while, like just clustering, nearest neighbors kind of style baselines, and for each particular problem domain, you have like baselines that actually do very well and are very good for the task, like bags of words plus a classifier instead of trying to put a RNN through your textual data. These kinds of things are important because they are easy to do. They're more efficient than like your typical like big hammer neural network, and they probably get like the neural network probably doesn't have any more advantage for your problem. So it's very important to construct the baselines first and making sure you know like what it means to be more accurate than like the easy methods. I think that's the end of the first 45 minutes of the lecture, and we will take a break, and then I will talk about two other topics next, which are the problems you get at scale, which are typically engineering problems, like how to make sure your hundreds of GPUs are satisfied, or like all of these things that you probably would see in the real world at maybe a reasonably large company. I will also talk about data engineering problems. Like most things that people don't talk about are like, oh, my data loader is kind of slow, but then there's no research paper that's published on like how to make your data loaders faster. Like all of these very practical things I will talk about next. And yeah. All right, everyone's settling back in. All right. Okay, the next 40, 45 minutes or probably less. I didn't calibrate. Okay, so let's talk about challenges at scale. Okay. The things that are never taught at courses, almost never covered, but like what you'll run into almost immediately if you join a company, like a large company or something, is if you actually want to do deep learning at scale, there are like very hard engineering challenges. Let me tell you about like very, very basic things. Data sets. Let's think about it. So you in the homework you used MNIST and you used Cypher10. Did you use ImageNet? Okay, so let's think about ImageNet, right? So Cypher10 and MNIST, you created your data set and data loader, and like everything magically just like, you know, you downloaded the data set in like what is probably a few seconds to a few minutes, and then you loaded it up into your computer memory. Let's say you have 8 GB of RAM, like your Cypher10 completely loads into your memory in maybe a gig, and it's great. Without even going into like real world, very large, like super large data sets, let's think about ImageNet that you actually covered briefly in your course. It's 1.2 million images. It's about 250 gigabytes in a compressed JPEG. If you actually try to like uncompress it and load it into memory, it will probably be about uncompressed maybe like 2 or 3 terabytes. So you don't typically have 2 terabytes of RAM in your memory. So this is a problem. You would keep this data set, this 250 gigabytes, maybe on your hard drive. But then the question becomes, okay, what GPU are you training your neural network on, and how big is your neural network? Is the round trip of doing a forward and backward and the optimization of your neural network faster than actually loading the data set from your hard drive and then decoding it and doing the data augmentation. It depends on your data and your GPU. If you have a Volta GPU, which is like the latest NVIDIA GPU, and you use their Tensor Core, then their advertised speed is like 120 teraops, I think, which is very, very fast in translation. But typically, you would see about 1/4 of that practically. And if you have like a slower CPU that actually was running fine with your Pascal GPU, and your data loading was not the bottleneck, now you'll suddenly run into this data loading bottleneck. And actually, it also depends on like what hard drive you have. Do you have a solid state drive, which can read data much faster into your memory, or do you have some like older spinning hard drive whose like random reads are actually like slower? Like, as you know, in deep learning, you need to shuffle your data set, otherwise like you're probably going to just overfit to a particular label. So these things are details that actually start mattering once you try to train anything at a reasonably normal scale, I would say. Like, they're not like toy data sets. And also, like, if you join an organization that has like 50 people, each person you wouldn't want them to have a copy of the data set on their local computer. Like, you'd want all the data sets to go into some network storage, especially if they're large, and then like all the training jobs can use that network storage. Now, okay, like what bandwidth does that network storage have to have to your like GPU machine? Like, can you read off like very fast from that? These are actually like very practical, normal day-to-day problems. The solution to that is actually, these days, deep learning frameworks have provided solutions to that. In PyTorch that you have been using, what we take care of you is doing things like multiprocessing, where for each of these data sets, you can simply fire up multiple background processes that are loading the data sets on the fly from disk and then augmenting them and giving them your main process, which has a GPU training. But this can be bottlenecked by, let's say, you have a network storage that is actually too slow compared to your GPU. These are engineering challenges, especially around data, that you will run into, and like no one talks about it, no one really like blogs about it or writes a paper about it. It's just once you actually like get dirty with your code infrastructure, you're like, oh shit, like something is slow. That's something you should keep in mind, especially if you transition to doing deep learning for anything practical. You might be thinking your GPU is slow or your model is slow, but it might just well be your data set is actually the bottleneck. Next is typically what we ask ourselves are like, how to keep the GPU occupied. So GPUs are typically very fast, and they're almost always bandwidth bound these days, except for like things like convolutions and gems. And what I mean by bandwidth bound means the rate at which you can take your data from your memory, put it into like your register, like your actual like core to do some math, and then take it out of the memory. That is your memory bandwidth. That rate of like how fast fast, you can take it out of memory, put it into your register, and take it out. That's your memory bandwidth. And almost all GPU operations you do outside of convolutions and maybe multiplies are bandwidth bound. They're not actually compute bound. So if you have a GPU that's advertising itself as I can do 120 teraflops and you're not doing a convolution, then you're not using 120 teraflops. You're probably using as far like whatever is the memory bandwidth that you're being bottlenecked by, and that's much slower. It's like a terabyte a second. It probably comes out to like 1/10 or like even worse. So that's the problem here is how do you keep your GPU occupied? And in deep learning, as you know, we do this thing called mini batching. So instead of actually taking sample by sample and sending it to a network and back, we simply take like a batch of samples and send them to the network and then back. And mini batching is actually not great from an optimization perspective. SGD, like pure SGD with a batch size of 1, theoretically at least, is supposed to work better. Now, with things like batch norm that we covered in the course, mini batching is helpful, again, from an optimization perspective, but the reason we started doing mini batching is because we need to keep the GPUs occupied. We need, like if you run like the GPUs like top tool that shows like how much it's being used, you want it at 100%. Make sure like it's being used all the time. The other thing is how to simply transform the bandwidth bound code to compute bound code. So instead of taking your data from like your global memory to registers and doing a very tiny operation and then putting it back into global memory, what you can think of is, let's say you have like a nn.conf2d followed by a nn.relu. Can you simply do the nn.relu as soon as the conf2d is finished, but while you're still in the register, so that you can save the transferring back to global memory, like you can say one trip in memory. So we do think of how to do efficient kernels, especially around like fusing operations to make them more compute bound rather than memory bandwidth bound. And this actually can practically make quite a big difference. You could get like 20-30% speed ups or even more depending on your particular problem. And the other thing is also like optimizing your kernels, right? So if you actually like it's not covered in your course typically, but if you actually sit and write down a convolution kernel to compute things, either on the CPU or the GPU. You start off, you write it, and you compare it to like what is available in PyTorch. It would probably, like my estimate is whatever you write will be 100 times slower. Because like the most obvious thing people will do is you would write the convolution in the time domain instead of the Fourier domain, which is more effective. And secondly, you wouldn't use all of the like hyper-optimized assembly code that some engineer in some corner has done and baked into like efficient libraries like cuDNN and KLDNN. So the other thing we do that like actually applies, like if you're running a project with say 30, 40 people that will run for 2 years, you'll be thinking about, oh, what are the computations I'm running in my model, and can I write a more efficient GPU kernel for this? Because like 20% faster speed on my model over 2 years would probably save like a lot of man hours of like staring at the screen for the last 2 steps. And then comes like the Facebook and Google scale problems, which are like, okay, I don't have one GPU, I have hundreds of GPUs. Like, how do I now keep these occupied? So if you train your on MNIST or SciPar, you train a small connet, maybe like like 32 feature maps in each layer, and it probably takes like a few minutes on your laptop. But if you start doing ImageNet or something, right? So if you take a ResNet 50, which is a very common model these days, even in academia, you take a ResNet 50, you take a single Pascal GPU and train it on ImageNet, which is like even like forgetting industry scale, like even in academic circles, this is very common if you want to get a vision paper published. This will take you like 2 or 3 weeks, or like maybe now it's like 1.5 weeks or something. But it's just like whenever you kick off an experiment, you want to wait 1.5 weeks to get the result and then like find out what to do next. Or maybe if you have like 8 GPUs available, can you simply train using all 8 GPUs at once? And so like generally doing like a few GPUs, like 4 or 8 GPUs, you can simply scale the mini batch size. So let's say you use 32 images per GPU to do your training. You can simply say, okay, if I have 8 GPUs, I will use 32 times 8 number of images, and then split the images over each GPU, and then do the forward, backward, and like the optimization. I will synchronize my grades. That's easy peasy, it converges well. But then, if you actually like try to do this for 80 GPUs, you will notice that your networks simply won't converge to the same accuracy. Like if you simply multiply the batch size by like 10 times, then your standard out of the box, what you learned, momentum plus SGD, trick won't work. You will get like lesser accuracy than you would get if you simply did like a smaller number of images per batch. So like multiple people pursued this problem, how to simply scale up the batch size to some ridiculous number and still have the convergence of the networks work out. So it's not a surprise that the 3 papers I'm going to present, which are the most popular, are from Facebook, Google, and NVIDIA. The first one, this is from Facebook. It's an attempt at simply scaling the ImageNet training to do batch sizes of up to 8,000 images per training for mini batch, and doing 8,000 images per mini batch, and then using 256 GPUs, you can train ImageNet on I think ResNet or something, ResNet 50 in 1 hour, compared to like 2 weeks or whatever the number was back then. And the guiding principles in the paper are around like how to, when you scale up to more number of images in your mini batch, how do you scale your parameters like your learning rate and your momentum and your weight decay and your general loss function, like all of these things? How to make sure you scale them in a very structured and known way so that scaling up the batch size doesn't get you lower accuracy. Like these are like very important but small details, and that's the first paper. It came out like sometime last year. And another paper, this is from NVIDIA, this is called the LARS optimization. It's the layer-wise adaptive learning rate optimization, where they want to do like even larger batch size. I think they do like 16K, and I think they've attempted like even larger batch sizes. So typically 16,000 images in each of your mini batch compared to like the typical 32, but you And so like you're using more GPUs, maybe you're using 512 GPUs or 1024 GPUs, something like that. And they actually have a, they try to, so you know how your neural network has like a number of parameters. Let's say your typical convolutional network, the resonant 50, I can't remember the exact number, but let's say it has 1 million parameters, right? So for like you use one learning rate number to do the SGD step. That is like weight new equals weight old minus learning rate times grade. This is the SGD step that you use. And if you have momentum, you have like some additional terms. So this particular step uses a single learning rate for all of your weight parameters. But there's a lot of literature in neural networks where you adjust this learning rate per parameter. So you say, oh, actually this parameter is not changing that rapidly. So you compute something. There are like very traditional methods where you compute the diagonal of the Hessian, and then you rescale the diagonal of the Hessian of your network, and you rescale the learning rates per each parameter based on like how rapidly the network parameters are generally changing over like the last few mini batches or so. It's sort of like intuitively you're trying to accelerate the learning rate of parameters that are moving slower and decelerate the learning rate of the parameters that are moving faster. Like you're just trying to do some adjustments so that everything learns like at the same rate or something. So with the large batch training, these guys actually found a layer-wise learning rate adaptation thing. It's actually like very simple to implement in practice, and I think they have the largest, like we can scale up to this amount of batch size compared to like all the papers I've read. And the last paper, this I think came out last year as well. This paper has another interesting take, which is saying, okay, actually you don't need to adjust your learning rates or anything like that. You don't need to change, you know how when you do your training, I don't know if you did this in your SciFar or MNIST training, but once your loss converges to, like once your loss slows down in like reducing, you step the learning rate down so that like your loss converges like much faster. That's something people typically do. They have these learning rate schedules where like, oh, after every 30 epochs, I will like divide my learning rate by 10 or something like that. And some people have like these even more complicated schemes that are like, oh, if my loss hasn't changed in like the second order delta by this factor in like the last 3 epochs, then I will like just reduce my learning rate. Like they have all these weird schemes, and people do all of this. And Google, they just said, you know, instead of actually like decaying the learning rate, instead of reducing the learning rate over time, simply increase the batch size. Just like use more GPUs as you get closer to convergence. And that's an effective and like easy way to like use more parallelism and get faster training. And they report, oh, we train a resonant 50 on ImageNet in under 30 minutes, which is like even better. And I think the latest number to this overfitted benchmark is you can train on ImageNet using resonant 50 in something like 12 minutes. So if you're a researcher from like 5 years ago, That just sounds impossible. And it only applies to you if you end up working for a place which has thousands of GPUs, and there's like very few places in the world like that. But these are things we see at scale, especially as like researchers are very impatient people, and also like generally you have deadlines that you want to meet, and you just want to have as fast training as possible regardless of like the cost or something. So the last thing I wanted to talk about is CPU a bottleneck? So whenever you think about how you drive all of these specialized hardware for neural network training, whether it's a GPU, a TPU, or let's say some new chip comes out, one of the things that's important to know and notice is like your code still starts invoking from the CPU. So yes, like you're actually launching some like kernel to run on the GPU, but you're issuing the command on the CPU, and the CPU then talks to the GPU driver that's also again being run on the CPU, and the GPU driver then sends some like microcodes to the GPU to say, okay, actually do this computation. On a typical NVIDIA GPU, each GPU kernel call takes about 7 microseconds. 7 microseconds, 7 to 10 microseconds. So if you're actually doing some computation that takes lesser time than 7 microseconds on the GPU, which is actually not atypical, then your bottleneck is the CPU. It's actually not how fast your GPU runs, it's just like how fast your CPU can queue the kernel. And like forgetting the GPU driver latency, you have like other factors like, oh, how fast is Python? Like if I write a Python for loop that queues a lot of kernels on the GPU, like each Python call will probably have about 1 microsecond of overhead. So like, okay, and now will Python become my bottleneck? So like all of these things are important things to remember and consider and keep in mind whenever you run your project at scale. Next, I'll talk about problems that are typically associated with not with research, but with production. By production, I mean, let's say you take you have a neural network that you have trained, it works great. Let's say you have a neural network that takes in an image and then like repaints it like the style of Picasso or something. It's a style transfer neural network. Then you're like, oh my God, like I trained this thing, it works great on my computer. I want to now create a mobile app that actually like does the same thing so that I can like put it on the App Store and sell it. You want to take this neural network that runs on your computer, but then you want it to run as fast as possible on your phone, or like you can take this neural network and make a web server backend for it, and then you can serve some like HTTP API that serves your model to some like front-end app. So what is actually different about production from research or like from like general day-to-day hacking is like one of the things you might want to do in production is you might want to take your neural network and then plug it into a much larger app. Let's say you're building a game, like a typical PC game. It's all in C++. You don't want just your neural network part to be in Python and have that dependency and like, you know, you don't want to do that. You simply want to say, okay, I just want to take my neural network export it to some format so that you can simply integrate with my much larger C++ project. This happens all the time as a request. Like if you're running a larger project where like your machine learning is actually only a small part, this is very common request from the developers. The second thing is whenever you think about shipping to mobile, like as the example I gave, you have like typically 6-7 generations of iPhones like still around, and you have like 10 generations of Android phones that are most used, and you have like hundreds of models of phones in general use, and each of them has a different quirk. And each of them has like different optimizations you can do to make things run faster. It's all of that optimization, especially at Facebook scale. If you're shipping your app to run on like, I don't know, like 1 billion or 2 billion phones, then like optimizing it to run even like 2% faster on mobile like saves a lot of people a lot of battery. Right? Like the other part is like, let's say like you're not running it on mobile, but you're running it on servers as well. If you're running like 1 billion or 1 trillion predictions, like a forward through your neural network every day, even saving 1% of the runtime is actually like a lot of money and time saved. So the kind of optimizations that you generally don't apply in like hacking on your laptop, like you don't care if your program returns in like 40 seconds or 39 seconds. It's like, okay, like what's the big deal? But in production, like that much of a difference is like a huge difference. Like at scale, it saves like a lot of money and time. So these are things that you generally think about and run into when you're doing things at scale and shipping products. And with PyTorch, what we ended up doing is we have an exporter. So in PyTorch, like what you've learned, the model, the neural network that you define is just a Python program, right? It's not actually like some program that you construct in some like weird graph language. It's just, you just have a Python program, and that's your neural network. Now, if you want to export it to some separate runtime, we have to somehow extract what this neural network graph is, and then put it in some other virtual machine that understands how to execute it, and which doesn't have the Python dependency. So we built a tracer that simply like runs your PyTorch model, and then records all of the operations that happen inside it, and then it puts it in this like intermediate representation that's describing what the graph that has been run. And then we export it into an industry-wide format called Onyx. It's ONNX. And Onyx basically has like front ends and back ends. It's like, it's this universal format that all the deep learning frameworks can export to and then import from. So PyTorch is an exporter to the Onyx format, and then you can take any framework like TensorFlow or Caffe2, which have a C++ only runtime, and then you can simply say run this model on just this pure C++ runtime. You can also do something that's even more direct for mobile, like Apple and Android now provide their ML-Kit and NNAPI, which, CoreML and NNAPI, which simply, they can take the Onyx format and then like hyper-optimize it for like their phones like CPU or GPU, and then you can integrate it into your app. So that's that's typically what we do to extract it to C++ only runtimes. And then for optimizing things and just doing general kernel fusion, we have like dedicated separate engines that typically do runtime optimization. And what these engines do are they take your graph that you have just defined, which is a neural network of some kind, and they figure out how to fuse most of the operations in this graph and even run them, instead of like at full floating point precision, run them at like 8-bit integer precision without any loss of accuracy. And typically this process like takes a little bit of time, and like it's very specialized only for inference and not for training, because in training you need the gradients in floating point. So there are products like the NVIDIA has a product called TensorRT that can take in an Onyx graph and then like optimize it and make it like 4 or 5 times faster. Like you have like different products from different companies that provide this like taking your model and like hyper optimizing for inference, and that actually like gives you a considerable amount of speed up, especially if you do quantization, like integer based inference rather than floating point based inference and stuff. So lastly, I wanted to run you through like some of the code. So I talked about, especially like over here, challenges at scale. I talked about how to keep GPUs occupied, for mini batching using multiple GPUs and stuff. I want to just take you through like the PyTorch ImageNet example that we provide. That's only like 300 lines long, but it encapsulates how to scale to like hundreds of GPUs or machines with ease. So this code might look pretty familiar to you, like it's Torch and Torch Vision being used. And so if you actually want to use distributed training, you simply have like these 2 arguments that you specify, I think these 3 arguments that you specify that you can configure. That's like, oh, I have these many number of GPUs that are actually sitting on multiple separate machines, and I want to give the masters URL so that like all the processes can talk to each other and synchronize with each other. And then we encapsulated all the engineering needed to scale up to like as many machines as you want within the torch.distributed package. So you take these typical arguments and then you create what you call a process group. That is a group of processes, figure out...
So it's multiple machines or multiple GPUs?
It's multiple GPUs and machines. It can actually scale up to like thousands of GPUs.
But so you would have to run manually several processes in the machine?
I will come to that as well. You don't have to run it manually either. So we call what is called a process group, which is like you launch, like say, as many processes as you have GPUs, and then they all form a group and they talk to each other. They have like a standard protocol that we established, and they talk to each other about like what URL each process is living on and what port it is communicating on, and then the total number of processes that are there. This is what we call a rendezvous. It's fully transparent to the user. And then the only additional thing that you need to do is this one line which says, oh, I have my model. I want to wrap this in what we call distributed data parallel. So whenever you give an input to this model, and input, like you do a forward, backward, when it does the backward, once all of the gradients are finished computing, it will simply sum up all the gradients from all of the machines among each other. So you will actually get like the sum of all gradients among all these processes. So effectively, you're doing like a much larger mini batch, even though you're actually doing individual processes, each doing their own mini batch. That's it. Question?
Where do you specify the machine names?
So you only need to specify the one machine name, which is what we call the master machine name. It can be any one machine in all of the machines, and you just have to specify like the IP address and like some port that you select for that machine. And all the machines will first connect to this one machine, and each of these machines know what their IP address is. They will self-discover that when they start, and then this one machine will provide like this rendezvous mechanism where it's like, oh, like I got like these 4 machines just connected to me. Now I will tell each machine the IP addresses of like all the other machines in this group. So you form a group, and then the tourists are distributed can then, oh, I don't have internet. Then you can actually send tensors from like one machine to another machine, or like you can send, like you have collectives that say, I want to actually take this tensor, and I know like all the other machines have tensors in this exact code location. I want to reduce among all of themselves, which means I just want to sum all of these tensors up among all these machines. Like they're like operations like these: send, receive, reduce. You have operations like scatter, which is like, okay, I have one tensor on machine 0, and I will send it to all of the other machines in the group. And there's gather, which is like, there is one tensor, like whoever does the scatter, all of the other machines will do a gather, which will sort of like collect the tensor that has been scattered. And for typical neural network training, our distributed data parallel container actually encapsulates all of the logic that is needed to like synchronize your gradients among all of the machines as well.
But this is the code for the front end, right?
This is the code for the front end.
But what need to write to run on the back end?
Like you're asking, how did we implement it at the back end? So in the back end, we have 2 parts. One is the rendezvous logic, which is okay, like it's this protocol that everyone connects to the main machine, the one machine, and this one machine tells everyone their IP addresses. We just implemented that in like a standard, like nothing interesting, just a small protocol. And then for the actual like sending all of the tensors from like one machine to another, it's just like these algorithms that have been described in literature for like the last like 40 or 50 years. It's called the MPI style programming model, where like if you want to exchange tensors between like say n machines and it's an all reduce, then like each machine shares like some part of the tensor with like the next machine, and like they do it in like this algorithm that optimizes for communication bandwidth that is actually needed to achieve this and all of that. Like there's nothing super interesting about this. Like if you take a distributed systems course at your university, then they will teach you all about it. And we use like some standard libraries that implement all of this for us as well, actually. So if you have like it, there are like much more detailed things here. Like if you have an InfiniBand card instead of an Ethernet card, the InfiniBand card, it's a special card manufactured by like this one company that does special interconnects. Then the bandwidth there is much higher than Ethernet. So we would want to prefer using InfiniBand to do our communications. So we have to then detect that and communicate with the InfiniBand driver that like, hey, you exist. What is your, like, we measure some effective like link speeds and all this like boring engineering happens in the back end, but like in the front end, you get this really powerful model that's abstracted out into like 2 or 3 lines of code that can train your neural networks, like exchange gradients and stuff. I don't have internet here, but like if you want to actually like read more on the distributed documentation, it's like in the PyTorch docs, there's a torch.distributed section, and it describes like how to easily launch all these processes. We actually provide a launcher that can effectively launch multiple processes or multiple machines pretty easily as well. And if your academic class, if your cluster at the university uses MPI, like it usually has an MPI exec, we also describe, if you have MPI, then you can actually launch it in an easier form, like in this fashion. Like we describe all of that.
Which PyTorch is this? 04?
Yeah, we had distributed since 03, I would say, or maybe 02, but 04 also, yeah. So I think that's we're end of time, and if you guys have any questions, I'll be around for like the next 30 minutes, and we can chat. But yeah, whoever wants to leave can leave it.